Much of statistical inference is based on this idea of a sampling distribution. And the biggest thing to understand about sampling distributions is that they're no longer just a distribution of your data that you collected, but they are a distribution of a particular statistic, like a mean or a proportion that we were just looking at. So all of these processes that we'll go over in the next few chapters start with an idea of what we would do using pieces of paper. So we'll go over this process just very briefly. If we were in a classroom, I would actually do it, but we'll just do the computer simulated version of it here. The idea is this: we're going from the US states data set, and this is a data set that represents a population because there is a value recorded for each state, and it's based on census data. So there's a variable called physical activity, which represents the proportion of residents, or the percent of residents in each state, who do 150 or more minutes of aerobic physical activity per week. Now, this is a quantitative variable. When we see percents or proportions show up, we start thinking categorical. It's kind of a funny variable because if we think about how the data were initially collected, each person was probably asked how many minutes of physical activity they do, which would be quantitative. Then when it gets aggregated by state in proportion, or rather more than 150 minutes or less than 150 minutes, it becomes categorical. But when we represent it as a proportion from each state, it turns back into being quantitative data. But it's now quantitative data where it's one value per state instead of one value per individual. In any case, here is the idea of how we would generate a sampling distribution for a mean using pieces of paper. Imagine in a hat there are pieces of paper with all 50 states, and we select a random sample of 4 states, so we just draw 4 states. Then we go to our data set and we look up the physical activity variable and we find the value for each of the 4 states. We calculate the mean of those 4 values and write it down, and that gives us one value in our sampling distribution. Then we put the 4 states back in the hat and we mix them up again, and we just keep going until we get several of them, enough that we would consider it to be a distribution. So we'll simulate this process using a website that generates random states, and we will pull up the data set and pull out physical activity values. The first thing we're going to do is generate a random sample of 4 states. And we're going to use a link that's in Blackboard that takes us to a website that will help us generate a random sample of 4 states. So under section 3.1, there is a link to this website, and by default it gives us 6, but we can scroll down and change this to 4 and get 4. So we got South Dakota, Ohio, Virginia, and Missouri. Coming back to my little tutorial here, I've just written down those 4 state abbreviations, postal code abbreviations for those states. Now I'm going to open up the data set US states. I don't need to get it into StatKey just yet. I really just want to look at it so that I can look at the physical activity value for each state. If all I need to do is look at that data set, then I double click on it from Blackboard instead of downloading it and then uploading it. So coming back to Blackboard, I can scroll down to where my data sets are. And this one is in the lockbook. And I can come all the way down to US states. Should be pretty far down because it's a U. Okay, Now I'm just going to double click on this. And in here, I'm going to scroll over to physical activity and then look up these values. Now, I find it a little bit difficult to look things up when the first column doesn't freeze, so you certainly can click on this Open with Google Sheets link here, and Google Sheets will give you a little bit more control. In Google Sheets, I'm going to choose the View menu and choose Freeze one column. What that does is make it to where when I scroll over to the right, and I can keep scrolling until physical activity is right next to the state name, it keeps the states visible. So let's look up our 4 states. We've got South Dakota, with 53.7, Ohio is 49.5, Virginia is 51.9, and Missouri is 48.7. So we'll write all of those down. And once I have them all written down, I can calculate the mean. This is a sample mean, so I call it X bar, by adding them all up. 53.7 plus 49.5 plus 51.9 plus 48.7 equals the total, and then divide the total by 4 because there were 4 values in my list, and I get 50.95 for that. So we'll use the manpower of this class to generate a sampling distribution manually by going to a numeric response Google form and just entering that mean that you found. And then you can view the responses from your classmates by clicking on this link. This is showing responses from a previous semester, but we can add our responses to this list, and I'll clear out some of the old ones when we get some more new ones. And then we can start to see a distribution that gets formed from all of these sample means. And we understand that the values going into these bars are each a mean of physical activity values rather than each value being a single value for physical activity. But we're also going to do the same thing in StatKey and get a computer-generated graph that means the same thing that our graph means. So we're going to go to StatKey and first select this item here. Sampling distribution is the heading and mean is the link that we're going to click on. We're going to need to upload that US states data set and select the column physical activity, and then we will find the mean and standard deviation of the data set under the word population. But first, let's go ahead and get that file uploaded. Of course, you'll need to download the file first, but we've done that in tutorials enough times that I think we can go straight to how to upload it in. Sampling distributions for a mean. I'm going to click on Upload File and browse for where it has been saved on my hard drive. And usstates.csv is the one that I want. I am interested in the variable physical activity, so that's the one that I select, and I hit OK. Now the first place we're going to look is under population. This is as if we were just going to descriptive statistics for one quantitative variable. It gives us a dot plot, and it gives us a mean and standard deviation, n, a mean, a median, and standard deviation. But in particular, we're interested in that mean and standard deviation right now. We don't need to write them down. We can just refer to them. The mean is 50.734. The standard deviation is 5.51. They will stay on our screen as we go through this tutorial. So we need to first choose samples of size n equals 4, because that's what we were doing manually. We're just choosing to find means over 4 states at a time. And then we're going to click on the button that says Generate One Sample. So in StatKey, right here where we see a 10 under choose samples of size n equals, I'm going to click on that 10 and change it to a 4 and then hit enter. And I'm going to click on this button here that says generate one sample. Over to the right where we see the word sample, we can see a smaller graph that has the 4 physical activity values that are in the sample that was randomly generated. So we have 41.2, 42.1, 53.4, and 54.5. If you're doing this on your own, of course, your values will differ from mine. We can also see down here at the bottom that the mean of those 4 values is 47.8. And we can see here on our dot plot that 47.8 is the value that was plotted. So far, it's the only dot in our sampling dot plot, so it's also the mean of this distribution, but that will change as we start to add more dots. So we're going to write these 4 values down in our table. Our list of randomly selected values is the numbers we just read off: 41.2, 42.1, 53.4, and 54.5. And the mean of those 4 values was 47.8. Now we'll do this again. We'll write down all 4 values again. We'll write down the mean, and we'll do it 3 more times, writing down only the mean, just so that we don't get too tired of writing down values. When we do this again, we're not going to clear this plot. We'll go ahead and just generate one sample again. We can see that our sampling dot plot now has 2 dots. Each of these represents a mean, and that over here I have, I need to select my new dot instead of my old one to make sure that what shows up under sample is the one that I just created. So my 4 values were 50.9, 51.9, 56.3, and 64.1. I can see that just by luck of the draw, I tended to get bigger values this time, and so my mean came out a little bit bigger. But these means are still hovering a bit closer to that population mean than each individual was. So let's return to StatKey and generate 3 more samples. This latest one here was a mean of 52.325. This one is a mean of 45.825. And this next one is a mean of 52.15. So we're going to add those to our list. I have gone ahead and rounded these to the 10th place, just like my first 2 were. So we have now 5 values going into our sampling distribution. These are the values. Form a sampling distribution for the mean. The mean x bar with n equals 4, the distribution would be different if I had selected a different number of states to go into each sample. So we're going to start to fill in another table now, which will help us to keep track of all of this information. Note that I said we could find our population mean and standard deviation in StatKey under population, so we'll go back and get those numbers now. We also want the mean and standard error from our 5 samples. So right now we're looking at the population and at the 5 samples part of this table, because that's the distribution we just created. Our population values are over here under population, and our mean of this sampling dot plot is 50.78, as we see on the bottom, and we also see a summary up here in the upper right corner. The mean is 50.78. They're calling this standard error, which we're going to talk about in just a moment. I'm going to write that down as my standard deviation, so 3.965. So here are my recorded population values and my recorded mean and standard error of the sampling distribution with 5 samples. We're going to now create a sampling distribution with 100 samples and a sampling distribution with 1,000 samples and fill in this information again. We can do that very quickly now that we've got this process established. Back in StatKey, since we want 100 samples, we already have 5. We don't want to end up with 105. So come up to where it says Reset Plot, and that will get you started from scratch. Then hit the button that says Generate 100 samples, and we get 100 different means from that population calculated and added to our dot plot. We can see in my case the mean is now 50.64 and the standard error is 2.752, so that's the information I'm going to record. It's a little early yet to start commenting on the trends that we see in these numbers, but we can observe that the means all look pretty close to the same, right? We started with a population mean of 50.73, and my 2 sampling distributions both have means that are pretty close to that. We'll comment on what's going on with the standard error after we've seen a little bit more. So returning to StatKey, same thing again. I want to start by resetting the plot, and then I'm going to hit Generate 1,000 samples and accept the distribution that comes up from that. I get a mean of 50.776 and now a standard error of 2.681. So these are the values I'm going to record. And we can see that, again, our mean of the sampling distribution appears to be pretty close to the other means and is getting pretty close to the population mean as well. What might look like a decreasing trend in our standard errors is actually just a result of luck in this case. We can see we started with something close to 4 and now we're getting into the 2s, and that it does appear to decrease each time. But what's really happening with our standard error is that it is just stabilizing. And we can see by going back and generating another 5 sample distribution that we wouldn't expect it to come out larger, like close to 4 again. That was probably just luck. We could generate several of those and it'll just hop around a lot, because with 5 samples, there's a lot of different ways that this could possibly come out. So that is actually a stabilizing effect rather than a decreasing effect. So let's come back here, reset the plot, and generate just 5 samples again. We can see that this time we get a standard error of 1.485. So this time we got a standard error that was very small. There's a lot more luck of the draw when you're only generating 5 samples than if you're generating 1,000. So that's a stabilizing effect that we see as the number of samples increases. On the other hand, we will see a different effect when we come back through and change our value of n. We are going to generate just the 1,000 samples distribution now with n equals 10, meaning that this is taking 10 states for each sample mean. So let's come back to StatKey, reset our plot, and come back to where it says choose samples of size n equals, and change that back to 10, which was the default value when we started. Just generate 1,000 samples to get a distribution. We have a mean of 50.705 and a standard error of 1.559. So adding these to our table, we can see we're closer than ever now to the population mean. With a larger number of states in each sample and a large number of samples, we're going to get pretty close to that population mean. And we can also see that we have a very small standard error compared to the standard errors that we were seeing with n equals 4. So our real takeaways from this are the following. Increasing the number of samples. There's 2 things we want to make sure we're distinguishing between. One is the number of samples, the other is the sample size that goes into each sample. Increasing the number of samples, so that's going from 5 to 100 to 1,000, all that does is make things stabilize. increasing our sample size, going from n equals 4 to n equals 10, does actually affect the standard error. So I've written down a brief summary of that. Increasing the number of samples, that's just more dots in the dot plot, more values over which that mean and standard error are calculated. All that does is help it to stabilize. But increasing the sample size using 10 states instead of 4 states, for example, in each sample, it doesn't change the mean, but it does cause the standard error to decrease. We get a smaller standard error with a larger sample size. And that language change from standard deviation to standard error is one that I glossed over initially in the middle of the tutorial, but we really change this language as soon as we start talking about a sampling distribution. Think of it this way. When we talk about standard error of a statistic, the context is that we are trying to estimate a population parameter with a statistic. And therefore, it's the error introduced in that estimate. And that's why we start calling it standard error instead of standard deviation when we're talking about a sampling distribution. So this is the idea behind that language change. There's some error involved in the process of estimating a parameter with a statistic. This distribution gives us some picture of how much error would be involved in that process, and that's why we refer to the spread of this distribution as the standard error of this process as opposed to the standard deviation. It is still correct to say standard deviation of the sampling distribution, but we generally can leave out the word sampling distribution if we refer to standard error and just say the standard error of X bar, for example.